Hello everyone, welcome to my channel again. I am going to solve a typical but slightly more challenging projectile motion problem. I will solve it basically just using your kinematic equations. It will be two dimensions, but it's going to be a ball that is thrown to the right and downward from a height. And we're going to determine basically its initial velocity given its hang time and the angle that it's fired at and the height from which it's fired at. So let me turn on my, let me share my screen so you can see the actual problem I'm talking about, and then we'll solve it. So here's the actual problem, and I've stated it in words, but I've also drawn a nice diagram. Hopefully that clears everything up. So it says a projectile, let's say a pumpkin, is fired at 15 degrees below the horizontal from a height of 100 meters. A, ignoring air resistance, what is the initial velocity of the ball if it takes 3.85 seconds to land? Okay, so they're wanting to know what is that V0. It's going to take from here to here, the whole hang time is 3.85 seconds. B, how far horizontally will it travel before hitting the ground? So they want to know X, this distance from right below where the ball was, or the pumpkin was fired, to right where it hit the ground, and then see what will be its velocity, the magnitude and direction just before it lands. So I'm asking what's the magnitude of this vector, and maybe what's this angle, which is the angle below the horizon, because we expect it's going to be at that angle. Of course, the farther it falls, the closer it gets to falling vertically, because basically vertical is when the vertical component of velocity is infinitely larger than the horizontal component of velocity, which of course never happens, but it gets closer and closer to that. So our job is to go determine what this initial velocity is, how far this goes, and then of course the final velocity, which will get an X component and a Y component, and then we use some trigonometry to figure out the angle, and we'll use Pythagorean theorem to get the actual vector. So let's stop sharing our screen. I think everybody knows what the problem is and what the numbers are. So let us now start by sharing my document cam and solve the problem accordingly. So what we have is some initial conditions that we were told. I'm going to draw my coordinate system as if the origin is right where the pumpkin was fired. So I'm going to call this the x-axis, and I'm actually going to call down the positive y-axis. Okay, and then I know it was fired from a height of y0, or excuse me, a height of 100 meters. And I'm actually going to call that the final y position. Okay, so that's this distance right here. From here to here is the 100 meters. Now it's going to fire and land like this, and I'm calling this distance right here x equals question mark. And this is my final velocity v, and I'm going to find out what this angle phi is right there. And I also got to figure out the initial velocity v0, its magnitude is what? And what we know is this angle right here is 15.0 degrees. And we also know that t, when it lands, is 3.85 seconds. So let's write down what variables we have. We have the initial height, y0 is equal to 0. The final y coordinate, of course, would be 100. By calling that a positive 100, that means our acceleration in the y direction would equal positive 9.80 meters per second every second. Our initial velocity is in the y direction would be v0 y is equal to v0. We can see in the y direction would be sine 15 degrees. So that's some of the stuff we know about the y dimension. We also know, of course, t final is t hang time. It's really the whole time it's in the air. So it's not exactly what we normally treat as hang time, but we'll call it hang time, is 3.85 seconds. We also know that x0 is equal to 0. And these, of course, are meters. But the final x is equal to question mark. That's what we want to know. Of course, that corresponds to a time t. We also want to know v0x. So v0x you can see would be this component right here, and that's a cosine. So you get V0 times cosine 15 degrees. Again, the time counts for both of those. And that's pretty much it. We should actually find Vx, which would be the x component of velocity at the end, and Vy, which would be the y component of velocity at the end. And what they are really is this vector. That guy is V0x. And this guy, which just runs into the bottom here, is V0y. So we've got to figure out what those are. Or excuse me, I shouldn't call them zero. They're just Vx and Vy, which is those. Okay. Boy, that green does not show up too well on there, does it? Okay, I'll try to write with it sparingly. And all right, so let us start. What we know is our kinematic equations, and a lot of learning physics initially in terms of kinematics is just knowing your equations. I want to find, for instance, not the time, which is often a challenge because you have to use a quadratic formula and all that good stuff. But in this case, I'm actually wanting to find the initial velocity. And really, what's dictating all this is how long this ball can stay above 100 meters, or this pumpkin or whatever can stay above 100 meters. So the equation I'm thinking about using is y is equal to 1/2 a sub y t squared plus v0 sub y t plus y0. In this case, the only acceleration we're dealing with is the a sub y, which is the positive g. So we really don't have to subscript it like that anymore. But what I can say is I know the final y will be 100. So I'm going to say 100.0 meters is equal to half of 9.8, which is 4.90. So I'm going to say that's 4.90 meters per second every second. Now, that times 3.85 seconds squared. So now I've got the 1/2 the a and the t squared, plus, now I've actually taken time to calculate what the cosine of 15 is and the sine of 15 is. So the y component is actually going to be positive. Now, when you're thinking about this, what you're thinking of, look at this equation. Y is the distance away from the origin. If you want to figure out the signs, you want to think which one of these contribute to the pumpkin getting further and further away from the origin. The acceleration downward does, because it's going to move a distance of 1/2 at squared for every second t, just because of the acceleration. So that's going to make this y bigger. This v0y times t, that's how fast it would be moving if it had no gravitational acceleration. And that, of course, is downward, as we can see here with these components. We can see that this one, oh, I drew it too big. Anyways, I'll draw it bigger, and that's okay, just so we can see it. So this is V0x, and then V0y is downward like this. And under that circumstance, we'd call V0 really to be something like this vector. So it's all that length. What you see is this velocity has a tendency to make that y get bigger. So that should have the same sign as this thing, which was making the y get bigger. And of course, this would too if it was farther away on this side. Now, if this one was farther away on the other side, this one would be negative. So that's some of the ways you think of it. I like to think of it just in terms of vectors. And I know the vector acceleration points down. I know the vector initial velocity points down. And I know that I chose downward as a positive direction. So they're all positive. So either way you think about it, that's it's okay. Eventually, you're going to have to think more in terms of vectors, especially for the second semester of these courses. So it might be best to get ready for that. Now, the V0y times t, it turns out that the sine of 15 degrees is 0.2588. So I'm going to say 0.2588. That's 0.2588 in case you can't read it that well, times V0, which is what we're wanting to know, times 3.85 seconds. And then the initial height was just 0. So now what I can do is I can rewrite this. I'll say 100. You see how all the meters are, how all the units are working, meters per second per second. That's going to be having those seconds removed by multiplying by seconds squared. This one's meters per second. This one has no units, and this is seconds. So I have to have a meter per second here for this to make into meters to be added. So right now, this number times that number would in fact be just seconds, whereas this number times that number would be meters per second. So when I multiply all this, I get 4.90 times 3.95 times, or excuse me, 3.85 times 3.85. So I did that 4.9, remember, comes from 1/2 of 9.8. So I could do 0.5 times 9.8 times 3.85 squared. And when I get that, I get 72.63, carrying 1 extra sig fig. So this quantity right here is 72.63 meters. So I'm going to now say 72.63 meters. And then plus, if I multiply 0.2599 times 3.85, then I can get just a 0.9964. That's 0.2588 times 3.85 seconds. This was meters. I was going to keep off the units, but now that I'm gotten this mess, I decided to go ahead and do it this way. V0, and then plus the 0 meters as well. So we see everything works dimension-wise, everything works mathematically. What I have to do is subtract 72.63 from 100. So 100 minus 72.63. And that gives me 27.37. Meters is equal to 0.9964 seconds times V0. Notice how I drew an arrow to represent the next line. If you just stuck another equals on here, you're sort of messing up, because you're saying 100 meters is equal to this. That's not really true. So it's better to not have floating symbols in space and stuff like that. Actually take the time to write the line again, where I've now subtracted 72.63 from both sides, and I got 27.37 equals what was left. Okay. Now, finally, I can figure out that the velocity initially is equal to 27.37 meters divided by 0.9964 seconds. And I believe that should be 27.47. So let's double check with my calculator. 27.37 divided by 0.9964, which gives me 27.47 meters per second. So that is the initial velocity. I've carried 1 extra sig fig. And when I say velocity, what I really mean is that's the magnitude of the initial velocity is 27.47. Of course, if you wanted a vector quantity, you have to say, break it into an X component and write it next to an I hat, or break it into a Y component and write that next to J hat. Or you just say, this is the magnitude at 15 degrees below horizontal. So really all we're looking for, since I gave you the 15 degrees, was the magnitude of this one. So that's part A. Now, part B is actually pretty straightforward, because part B was asking us how far does it make it to the left, or excuse me, to the right. In other words, what's this distance right here? Remember, you've normally seen those pictures if you're taking this course right now. You've seen those pictures where you drop a ball from a height, and at the same time you fire a ball horizontally from that same height, and that each interval of time, say 0.1 seconds later, the two balls are the same height. 0.2 seconds later, the same balls are the same height, or the two balls are the same height. 0.3 seconds later, the two balls are the same height. That just shows you that the horizontal motion and vertical motion are really disconnected. The horizontal motion, in fact, has no acceleration. So its average velocity is, in fact, its only velocity. And its only velocity, of course, is V0 times cosine 15. So what I have for part B is all I have to use is x is equal to x0 plus what would normally be the average velocity. But in this case, the average velocity is the velocity times time. So the initial x, obviously we started at the origin. So initially the x position was 0. And that's why we also took the time to put these variables and assign them quantities. So this is 0 meters plus. Now we've got to take that 27.47 meters per second and multiply it by cosine 15 degrees. And then multiply that by the time, which is 3.85 seconds. And what we get is, I'll double check on my calculator just to make sure. So I'm going to say 27.47 times cosine. I'm going to go over here and do cosine 15. And then I'm going to say, oops, not that. I got to come outside of the parentheses, say multiply, and 3.85 seconds. And that gives me 102.2. So this is 102.2 meters. That's X, and this is part B. And in fact, I was multiplying 3 sig figs by, this was 15.0, so that's 3 sig figs, and that's 3 sig figs. So that's one extra digit there, and that's the answer to part B. Now, part C, we're asked what's this final velocity. So I know the x component of velocity is not going to change. So that 27.47 times cosine 15 is going to be it. The y component of velocity, however, for each second it's aloft is going to increase its downward speed by 9.80 meters per second. So it started off at v0 times the sine of 15. And then after that, it's going to become something quite large. So the equation that can handle, or one of the equations that can handle that is V is equal to V0 plus AT. In this case, I just subscript everything Y. And of course, we didn't need to do the A sub Y because that's the only acceleration. But we can go ahead and figure out what the V0Y is. That's going to be the 27.47 meters per second times the sine of 15.0 degrees. This time we'll put the 0.0 so we wouldn't have to remind ourselves what that it's 3 sig figs. So that's just the V0y plus, notice those two are both trying to increase the velocity, so they should both have the same sign. The velocity was initially going downward in the y direction. The initial velocity therefore is helping this go downward, and the acceleration is helping it move downward as well and increase its speed downward. So those two should definitely have the same sign. Or again, just think in terms of the vectors, the acceleration vector points downward and the initial velocity vector points downward as well. So in this case, I'm going to say 9.80 meters per second every second times 3.85 seconds. So now I can get 27. I'm going to go ahead and compute this just so we'll know what the initial velocity in the horizontal or in the vertical direction was. 27.47 times trig function. I'm going to use sine 15. And I see that 7.10 or 7.110, carrying one extra sig fig, meters per second is the initial downward velocity. Plus it's going to accelerate by 9.8 times 3.85. That's going to give me 37.73 meters per second. So that new final velocity would be, I'm going to go ahead and add the 7.109 or 110 and the 37.73 and realize that I only have one sig fig after the decimal place. So this is going to be 44.84, and that's our doubtful digit is the 4 there. So that's meters per second. So that's the V0 or excuse me, that's the Vy, final initial final velocity of the pumpkin in the Y direction just before it hits the ground. The Vx is something we also need, but that's just Vx is equal to 27.47 meters per second times the cosine of 15.0 degrees. Obviously, the cosine of 15 degrees is a lot bigger, so that's going to make a much larger scenario. And let me break this up since I drew it right beside it. It's going to look confusing. So I'll split that off there so everybody doesn't confuse this as part of that calculation. So now that we have that, 27.47 times trig function cosine 15. Whoa. That should be 3 sig figs. That gives me 26.53. So this one's 26.53 meters per second. You can see that the y component is quite a bit larger than the x component now. And if I draw my coordinate system again, what I'll have is there's the x direction. This is the positive y direction this way. I'm going to draw a positive x component using my green line for the vector. And that's V0, or excuse me, that's just Vx. I keep wanting to put a 0 on it. That's just Vx, which is equal to 26.53 meters per second. And then at the tail of that, I add the head of something that's nearly twice as long. Actually, I might have exaggerated a little bit. This is Vy, which equals 44.84 meters per second. So I now have two components. I just got to reconstruct or build the vector. And that means figuring out what the magnitude of the vector is, which is V, and finding out what this angle we named phi was. Well, V is just given by Pythagorean theorem. So V is equal to square root of 26.53. I'm going to leave the units off this time, but I want to mention something to you. If this unit had come out negative, if this component would come out negative, or that one, what you got to understand is you always put the whole component inside the parentheses. So if this was negative 26.53, the negative would be inside it, so that when you square it, it's automatically going to be positive. Same thing with this component. However, there are times when you use the Pythagorean theorem where you might be solving for something where it does end up getting a negative in there, but that's only because a squared plus b squared is equal to c squared. So if you're solving for b squared, that would be c squared minus a squared. That minus is supposed to be there, but keep that in mind. This one's 44.84. Okay, it's also helpful to keep an eye on exactly how big 26.53 is. So when I do this kind of thing, just to keep track of my sig figs in case, you know, an instructor happens to want proper sig fig work out, what I do is I do 26.53. I know that's got 3 sig figs. So when I square it, it should have 3 sig figs. So I square that and I see that 703. So it's good to the nearest whole number, because that's the 3 sig figs. Then I do 44.84. That should have 3 sig figs as well. I square that and I say, okay, well, this is supposed to be 2010.6, but it's only supposed to have 3 sig figs. So that's the thousands, the hundreds, and the tens place. So really, I'd have to actually round this sum of these two to the tens place. And see how many digits I got. So now let's add those two. I'm going to say that number plus the 703. Remember, this one's only good to the tens place. This one's good to the ones place. So I want to say enter that one. And now I've got the square root of 2.71 times 10 to the third. That's actually the tens place is the 1. So this is going to be the square root 2.714 times 10 to the third. And really, that's the tens place. So I really only have 3 sig figs now, which is okay. That's how many we were given initially. So I finally find, let's not write that over there. Let's write this down here. I'll say that finally the velocity is, and I'm going to take the square root of that number. And my calculator allows me to pull the last answer by hitting control this. So I get 52.10 is the final velocity. Why did I just do it again? So 52.10 meters per second is the magnitude of the final velocity. Now I can find phi by taking phi is equal to the inverse tangent. Notice tangent is opposite of hypotenuse. So that'll be 44.84, 1 extra sig fig, over 26.53, 1 extra sig fig. And when I take the inverse tangent of that, I get trig function tangent inverse 44.84 divided by 26.53, and that gives me a pretty big angle. That's 59.39. That's 1 extra sig fig. So V is actually equal to 52.1 meters per second at, you could just measure downward from the, in other words, clockwise from the positive x-axis. You could just call this negative 59.4 degrees. And that is the complete answer for part C. So 59.4 degrees with a magnitude of 52.1 meters per second to the proper number of sig figs. That is all well and good. That's a horrible looking second, but we've now solved the problem. Hopefully that helps you if you have similar projectile motion problems. The big majority of problems that students have with regards to projectile motion is, and kinematics in general, is knowing what the signs are supposed to be in these various equations and stuff. So there's, as I mentioned earlier, there's a couple ways you can look at it. If you think of everything in terms of vectors and think of which way those vectors points, if you have a good understanding of vectors, then the signs just fall out automatically once you make your coordinate system. However, if you're not that savvy with vectors yet, you just try to think, okay, what's the equation solved for? In this case, it was y. And do these things contribute to making it larger or smaller? Well, this contributed to make it a larger y, and this contributed to making it a larger y. And if this was positive, in other words, if this was down here below the x-axis, since down is positive, that would contribute to making it larger. So that would be positive as well. So you'd say positive, positive, positive. If, however, it started above, maybe I said the initial height was 110 meters above, and I had arbitrarily chosen the origin to be at 100 meters above, then that would be a negative 10, not only because the coordinate says that, but because that's actually trying to make that y smaller. So you can sort of think of whether the things in the equation are making things larger or smaller. And this is another case in point. This position right here, does this make it larger or smaller? If it makes it larger, then it's more than likely going to be a positive quantity. And if it's actually going in that direction that makes it larger, then this would be a positive quantity. If, however, this was making that x smaller because it was actually moving closer to x equals 0, then this would have been a negative. So that's some tricks to help you if you're having problems with thinking about your signs on kinematics. I hope that helps. Good luck and enjoy physics.